This video will present a very basic introduction to the new kinetic model in the Continuum's 9.0 firmware. Its intent is to give you a basic understanding of the core physical model that's at the heart of the kinetic model, show you how to generate and manipulate a simple sound to get you started, and then in follow-on videos go into more details on the finer points of its use. The kinetic model is an adaptation of the sound generation and processing techniques used in Christophe Duquesne's innovative Springsound app. Christophe worked with Lippold Haken and Ed Egan to integrate components of Springsound into the EaganMatrix. The kinetic model can generate a wide variety of sounds tailored for expressive control from the Continuum's fingerboard. For example, it can act as a resonating body, creating a variety of bell-like sounds. It can be a sophisticated noise source, creating anything from scraping to door creaking to mouth sounds to bowing noise to wind. Can act as a sound processor, a physical filter, a resonator, create distortion, and more. But it takes some understanding and especially experimentation to get the hang of it. Let me read the manual's introduction. The kinetic model is a state space model of a mass attached to a spring which is anchored within a one-dimensional container of viscous fluid. The output of the model is the position of the mass. The mass may be set into motion by the excitation input, which exerts a positive or negative force on the mass. The mass may also be set into motion by bowing, or by moving the anchor point of the spring attached to the mass, or by changing the height of the container so that its edge hits the mass, or by changing gravity, or other ways. The mass may oscillate due to the spring, or it may bounce between the top and the bottom edges of the container, or it may bounce along the bottom edge of the container. The padding parameter can be used to emulate deformation of the container when the mass bounces. Viscosity slows any motion of the mass. Alright, that's a bit too much to chew on to start, so in this video we'll just cover the basic classical anchored spring attached to a mass. This is universally used to demonstrate the fundamentals of simple harmonic motion, or harmonic oscillator. This is really what's at the core of the kinetic model, and then additional physical modeling functions such as elasticity and slipping friction are added to allow for the creation of an increased range of sounds and functions. So the first thing we want to ask ourselves, as some of us might be musicians who don't think about such things that often, is how can a spring's motion be directly translated into sound waves? Here's a great representation. I have the YouTube link in there that attaches a paint spray can to a large spring. It could have been a marker or some other drawing device, I guess. The paint is set to constantly spray. The spring is set into motion from its resting or equilibrium point, and the paper is manually rolled. It's easy to see how a sine wave results, a bit distorted because the paper is not pulled at a constant rate. That, in essence, is how the kinetic model creates sound, mathematically modeling the spring system and outputting the position of the mass, in this case the can's spray head, which is processed and finally translated into sound through the magic of digital to analog conversion. Now let's look at some of the parameters that affect the spring's motion and in consequence the position of that mass that represents the resulting sound wave. Before we get to EaganMatrix programming of the kinetic model, I brought up a spring simulation here I found on the internet. You can go to this website and play around for yourself. We'll look at the four main parameters that we'll be dealing with in our initial kinetic model programming. There are more available in the kinetic model, but to start we're just going to use these four. And those four are the mass of the object connected to the spring constant, that's the tension of the spring. We'll also look at the effects of gravity on the spring system, and finally damping. Damping would be the resistance of the system. In an open system like this, the resistance would primarily be air resistance. In our kinetic model, we have the system enclosed in a container filled with viscous fluid, so that fluid would be the main source of resistance. We'll start by taking gravity to zero, remove the effects of gravity, and take damping to zero, remove resistance. So once I set this spring in motion, it should continue in motion forever. The first thing we want to look at is how just mass and spring constant relate to each other. So the mass is set at its stationary equilibrium point. I'll set this into motion by bringing it down to a movable reference line, and I'll let it go. I set this so that a simple waveform is drawn when the spring is in motion, and you can see that the amplitude of the spring is basically equal to the distance I pulled it. This basically follows Hooke's law, which says there's a linear relationship to force and distance in a spring, which also would map here to amplitude. If I stop this and move the fixed line about twice as far away, I should get an amplitude because I'm applying twice as much force. That's twice as much as what I had before. You can see my amplitude is matching the distance that I pulled this. All right, now that we're in motion, let's see what happens if I increase the mass. As you can see, the frequency is slowing down. So let's increase our mass. We'll bring it down to a fixed point and we'll let it go. And you can see the frequency is much slower than if I had done the same thing with a small mass. Here I trace out the same amplitude pattern, but obviously the frequency is higher. That's the first thing to understand in our kinetic model. As we increase the mass, everything else being equal, we're going to slow the frequency. How about spring constant? Let's set a relatively high mass and we'll set that into motion. And now let's change the spring constant and make it higher. You can see increasing the spring constant increases the frequency. Well, there's more tension on that spring, so it's kind of obvious. Decreasing the spring constant slows the frequency. Now if I increase the damping, that will slow the system down as it decreases amplitude as that mass tries to get back to its equilibrium point. So let's add a little bit of damping, and the system's slowing down. The amplitude is decreasing until it rests at its equilibrium point. Now, if I increase damping to a much greater value, the system will slow and come to rest even faster. Okay, so there's our current damping. Let's set a very high damping, and this should come to rest much faster. There, pretty much done. In the kinetic model, the viscosity of the liquid really provides our resistance, so viscosity is the parameter in the kinetic model that represents damping. Now, gravity. We'll increase gravity and see what happens just in the stationary system. As I increase gravity, my equilibrium point increases. Let me remove damping so we can see things better. I'll set this into motion. And now let me increase gravity and see what happens. The equilibrium point changes, the mass gets lower, but the frequency stays the same. And you can see that if this was in a fixed container, I'd be hitting the bottom, or if I have some stickiness that I've programmed, I might stick to the bottom, or the mass might be so heavy that the weight just stays at the bottom. You can set the kinetic model to react in some of those ways. So gravity can be important in your kinetic model. If you set it too high and start the system off, it might not give you any sound because basically the mass is pinned to the bottom of the container. Now there are a couple representations of this model. We looked at the web view where the anchor point was on the top and we had a suspended spring from that. Some of the documentation may show something more like this, where the anchor point is on the bottom and you can then apply the force from the top, applying it as a push down or a pull up. So EaganMatrix will allow you to define a positive or a negative force on this spring. In the matrix itself, this representation is used. The anchor is at the top, the spring is suspended. It doesn't really matter if the model is the same. The important thing is to understand the parameters that apply to the model. As in the web simulation, we're going to concentrate for this video on spring constant, mass, gravity, and viscosity, which is equivalent to damping we used before. There are a couple other parameters that can change, the height of the container, the anchor position, but we won't really work with those too much. Let's bring up an empty matrix. There are two possible kinetic model banks that you can define. Just select Kinetic Model 1. We're only going to deal with that in this video, but there's another one available. When you do that, if you click Properties, which it defaults to in this case, you'll see at the bottom this graphic view of all the parameters that can be set as constants, values that will stay as long as you save your preset, but these values are not directly controlled in the matrix. You can select up to 4 of them in the matrix, and once selected, then you can dynamically change them programmatically, and whatever values these turn out to be will be added to the values that are already set. Another thing to be aware of is if you set something, let's just set some of these to some values. If I inadvertently go to some other bank and come back, my values will default back. So just be careful. In this case, unlike when you type things into the matrix normally, if you go in and out of banks, your values can be lost. So if you're working on the kinetic model, save your preset regularly. So we'll start out using just 2 of the columns in the kinetic model. The first one is the excitation input. This allows you to create a force on your model. This can have a range of -2 to 2, and it can be set in various different ways. The other parameter we'll look at is frequency, and this is standard frequency input in kilohertz. As we'll see, frequency in the kinetic model has to be thought of a little differently than when you use it in other banks, because it's much more flexible and maybe not always exact. As we saw before in our simulation, you can do a number of things to affect frequency. So if you have some dynamic control that's fiddling with mass or spring constant or a few other things, you can change that frequency. It could be hard for you to even predict what frequency is going to be played at any particular time. But if you do make a setting and you want to keep it, and it doesn't match the frequency you're intending, there is a little control down here that you can set, this step frequency trim, that will allow you to set frequency, both coarse and fine, for a given sound that you're working on. So first we want to ask ourselves, how do we create a sound? Now there are a number of simple methods of creating impulses for exciting the kinetic model. Some of them are using a shape generator pulse on the force input. You can pulse the anchor. You can create shifts in gravity. You can create noise bursts of various kinds. You can use Z or differential Z, or you can use a shape generator that just specifies a positive or negative value that's predictable. We'll start with that one and also use some noise to begin with. So let's go to our model. We'll start by specifying a fixed frequency. I'll use 110 Hertz. As we said before, that doesn't mean that 110 Hertz is going to come out. That's just my base frequency. Now I want to pulse the excitation input of the kinetic model with a positive value to start that spring in motion. How would I do that? Well, we'll use a shape generator. We'll set that to 9 times 9 for frequency, so a very high frequency shape generator. We'll gate that with a press on the fingerboard. We'll create a formula that will use that shape generator. We'll set that to a pulse because I want that shape generator to pulse, and I want it to do a single pulse, not continuous pulses, so I'll set this to single cycle. I'll set the formula on the numeric input to the kinetic model because I want to pulse it with a numeric value, predictable value, and I'll set that value to be the max 2.0. So when I press my fingerboard, I should pulse my kinetic model with a positive 2.0 value. If I wanted, I could put a negative force on it and pulse it negatively. The point here is I want a predictable input to start. Finally, I want to send that to the outputs. Now be aware the kinetic model can create a horribly loud noise if you're not careful. And because so much of using the kinetic model is experimentation, you will at times just create loud bursts. You could create a very high amplitude, constant sine wave. So as we always suggest, turn your gain down when you're experimenting with the matrix, especially with the kinetic model. We'll send out a value of 0.4, less than unity value. And now we'll go and see what the properties are. Our default properties are 0.2 viscosity, low viscosity, full height for the container, no gravity, very low mass, and rather low spring constant. So will that be the right values to generate a sound? They might not necessarily generate a sound. This isn't like an oscillator where I can put X in the frequency column and just send it to outputs and be very predictable in what's going to happen. So let's press the fingerboard and see, at least for this combination, whether it does anything. It gives me a kind of bass drum percussive sound. Let's bring up the sound a little bit. Try that again. Now you might think, hey, that's pretty cool, nice sound. But when we're starting to program the kinetic model, we want to know exactly what the kinetic model only is generating. And if you notice, I have the recirculator up pretty high here. Most of what we're hearing is that recirculator. So let's turn that down. I don't want that to confuse me. You might also have formulas that have persistence or interpolation on them. Let's take that off as well. Now let's give it a shot and see what we really created. There. Let's see if we can bring up a scope, and that is the waveform of what we created. You can hear it's a very shortened sound. Well, let's look at what we have here. Again, viscosity is low, but high in relationship to some of the other low settings we have. This is why that sound is cut off so quickly. Let's lower viscosity, make it really low, say 0.05, and see how that affects the sound. Whoa, now we have a much different sound. So here you can obviously see the damping was lessened and we have a longer time that the waveform is active. If we make this a very high viscosity, and so we should get a much shorter sound than we got originally. There, just kind of a quick thud. This was damped before the waveform really could even get going. Let's go back to our earlier setting. Something maybe in the middle. Remember that the model is a spring with a mass attached inside a container. This means that if you give the mass enough force, that mass will be hitting the edges of the container. We're sending in the max force of 2 for the input to this kinetic model. And the mass is low, and the spring constant's low, my viscosity is low. Let's quickly go back to the simulation. I'll set this on slow. We have something similar, a low mass, a low spring constant, low damping. Let me set this into motion. I'll give it the full force I can, and let's see what happens. That mass goes past the edge. So if this was our spring model, and we had something similar, our mass is going to hit the edge. Now that in and of itself doesn't mean anything bad. If you like the sound that results, and the mass is hitting the edges, fine. But sometimes you might want to optimize the sound where your mass is not hitting the edge. Big question is, how do I tell if the mass is hitting the edge? That's a very difficult question, and from the ear sometimes you can't tell. Sometimes you can hear some double banging that might be representative of it hitting edges. You can look at a waveform and perhaps that waveform is distorted up front, whereas if it wasn't hitting the edges, it might have a smooth attenuation profile. Another way to possibly detect that the mass is hitting the edges or possibly being driven too hard is to look at how it changes when you change your force on the model. We're driving this model with the max value. If we go to our scope, this is going from about 0.2 to 0.2 on our scope. If this was a normal spring and it wasn't being perturbed in any way, we'd assume that if I give this half the force, according to our linear formula we talked about, I should see about half the amplitude we have here. Well, let's give that a shot and see what happens. There, the amplitude really hasn't changed, and that's because the model is so low on those parameters that even though I've half the force, I'm still maxing it out. And I can go pretty low on this one because the parameters are set so low. Let's try go even a tenth of that. So let's go to 0.1. There, it really still hasn't changed that much. This model is so low on those parameters, I really have to set that force pretty low to have an effect. Let's try going down to, say, 0.02. That probably is enough to see a change. There you can see the attenuation profile is starting to change. So that's one thing to be aware of. You will be hitting the edges, but to start out, don't worry about if you're hitting the edges. Worry about the sound you're creating. Is it a sound that's pretty much what you want? If so, fine. I've taken our model and I've changed it a bit. If you notice, I raised everything a lot. Here I have a viscosity that's 0.33, that we had no gravity before. I've given it a little bit here. The mass is raised almost a half. The spring constant is pretty high. Let's hear what that sounds like. Similar to what we had before, a little wooden percussive sound almost. The waveform looks like this. This is a little more suggestive of what we'd assume a normal spring would look like with some damping on it. So now what would happen if we take this viscosity and we take it down to 0? As we saw in the simulation, when we took damping down to 0, the spring, once we set it into motion, went on forever. And the same thing will apply here, only what we'll get is a sine wave that will go on forever. Let's try that. Now look what I did there. I set viscosity high to get out of that constant sound. Very often you might set off a sound like that and get flustered and not know what to do. Obviously the first thing you can do is take your gain down, but you can also quickly damp the sound and it should go away. We've been using a positive force as an input to the kinetic model. We can use a negative force as well. If I do that, you can hear it's going to sound very similar to if I use a positive force. The difference here is that I can predict which way the model is being pushed. But I don't have to use a numeric value to trigger the kinetic model. I could use a noise burst instead. Let's lower that fluid friction, the viscosity. That will give me a more bell-like sound because the waveforms are damping slower. But now I'm on the noise line, and look at the amplitudes. They're all over the place. Before, we had a predictable amplitude because we were always sending in the same force. But with noise, it's a random value. And Christophe actually has this to say: when you use a noise burst as input, since a noise has positive and negative values, you alternatively push the model up and down. So the global level of the burst is not the main thing. The result of the burst will mostly be dependent on the final sequence of the level of plus and minus values. And since it's random, you won't have a fine control over it. Obviously, the randomness gives you, in one sense, less control, but in another sense, it gives you perhaps more musicality in some respects, and other nice things that might result from its randomness. Another thing we can look at is the speed of this pulse. Right now it's fast, 9 times 9 in terms of frequency of that shape generator. What if I made this much less, only 2? What's that going to do to the sound? There you can see up front, the pulse is a lot longer being fed in as force. So you have all this random energy coming in, and you can hear at the beginning the noise that's being fed in, whereas we didn't hear that before when we had a quick pulse. Of course, after that, we can see the damping profiles, what we expect. So playing with the timing of the burst also can be interesting and give you different kinds of sounds. Let's set that back, maybe a little slower than we had it before. But now let's talk about frequency. So let's change this a bit. Maybe we'll bump it up an octave. See what I've changed the fluid friction viscosity on that a bit to make it ring a little more. Now, the question is that 220 hertz? Sounds higher than that to me, but what we can do is let's create an oscillator with the expected frequency we want. We'll send that out with the standard Z function and see what we really have here. So as we saw, the mass, the spring constant, they affect the pitch. Depending upon how you've played with them, you might not know what pitch you're really at. So let's use our step frequency trim function. This allows me, as we said before, to do a coarse pitch adjustment using the NN option and a fine adjustment using sense. And what I'll want to do is set myself to the correct pitch. So there I've kind of calibrated my pitch, and if I now remove this calibration tone, I don't have to just play a fixed frequency. In fact, most times I'm going to want to use X or some X-like function on frequency so I can track my pitch on the fingerboard. If I do that, now I can play my sound. Now sometimes, depending upon the parameters you set, and if you have some dynamic motion on them, it will be hard to actually set a frequency that's going to map correctly. But this technique is a good one I've found if you want to try and calibrate your kinetic model. Let's look at these two nonlinear adjustments next. These can be applied to viscosity and to spring constant. They're not programmable in the matrix, so you have to explicitly set them with the dials in the kinetic modeler. So let's look at viscosity first. As a small aside, there are 4 basic types of friction, 2 of which, sliding friction and rolling friction, we don't care about in the kinetic model. That focuses on fluid friction, viscosity, which we're talking about now, and static friction, slipping friction, which will be covered in another video. On nonlinear adjustments, viscosity equates to fluid friction force, direction opposite to the speed, which is proportional to the speed. Here the viscosity constant, V, which is different from the spring constant, is expected to be fixed in theory, but in the real world it's quite unlikely that V is really going to be a constant. So the kinetic model adds the linearity parameter that changes the value of V depending on the speed. It is very useful, especially to get very long resonances. The linearity adjustment for spring constant adjusts K based on position, not speed. From the manual, viscosity defines the fluid friction. This creates our damping. This friction is dependent on speed. The higher the friction is, the faster the spring will stop moving. Note that also the spring will continue moving if the mass is higher for the same friction due to inertia. A viscosity of 0 is like vacuum, it gives us no resistance, where 1 is something like heavy oil. Now that nonlinear adjustment to viscosity, linearity of the fluid friction. When set to 0, center position, the friction is linear. If it is positive, the friction will be lower when the speed is small. If it is negative, the friction will be lower when the speed is high. This property is not accessible from formulas in the matrix. Well, let's see what it does from a functional perspective. First, we didn't say this explicitly before, but here if we have a viscosity of 0.14 with a mass of 0.7, we have a little bell-like sound. And as the manual states, if I make this mass a lot higher, we'll expect the damping effect to take longer to come back to equilibrium, and you can hear that heavier mass takes longer to go to silence than the lighter one did. Now, what does the nonlinear adjustment actually do to the sound when we raise it or lower it from the 0 position? Here's a graph of some sounds that I recorded in the scope with nonlinearity set to 0, just applying our fluid friction, our viscosity. As you can see, as viscosity is lowered, the damping effect is elongated and takes longer for that mass to come back to its equilibrium state. Basically, the sound rings longer. As I increase viscosity to 5, 0.5, 0.75, you can see the damping effect is faster, and the exponential curve that results in each case gets steeper to make that sound damp quicker. Let's assume we'll start with viscosity as 0.25, and we'll keep that, and we'll just change the nonlinear adjustment. So here's our sound that results from the base viscosity of 0.25 with no nonlinearity. And now we'll bring up the nonlinear adjustment, and you can see the effect that it has on the bass sound. It elongates as if we were decreasing the viscosity. So in effect, I consider this a trim adjustment that can fine-tune your viscosity. Now if we go in the opposite direction, we start with our base viscosity of 0.25 and we lower that nonlinearity, we make it negative, the opposite happens. It starts looking like we're increasing viscosity. The exponential curve steepens and the dampening effect increases. Here's our bass sound. If I increase that nonlinearity, that should take longer to damp out. And you can hear that. If I set it high enough, that exponential curve is going to be so shallow that this goes on for a very, very, very long time. Very much the same as if I'd taken viscosity down to 0. We've only been using a fixed frequency, and this nonlinear control, as we said on viscosity, is speed dependent, frequency dependent. I'm using X now instead of that fixed frequency. We'll play a few notes low, a few high. We have viscosity set low to begin with, and no nonlinearity applied. The high tones will damp quicker in any case. But when we apply the nonlinearity, the effect will be even more pronounced. So let's bring that up a bit. And now we'll play a high note. It damps slower, and the low one takes a lot more time to damp out because I've set this nonlinear adjustment. And if I make that higher, so this nonlinear control for viscosity emphasizes the frequency dependence on the damping. Now let's take a look at the nonlinear control of the spring constant. As we saw in viscosity, the nonlinear control affects damping. Well, spring constant we know affects pitch, so we'd expect this nonlinear control to have some kind of a pitch-related change. Let's go to the manual. The spring constant defines the strength of the spring. The higher the strength is, the higher the frequency you will get. The strength can be null. In this case, nothing calls the spring back to its anchor position. The spring linearity defines the linearity of the spring. When set to 0, center position, the spring force is linear. F equals kx, with k fixed, whatever the distance x from the center position is. That's that relationship we looked at before, where the force has a linear relationship to the distance. That changes now. If the spring linearity is positive, the spring force will be lower when distance from the center position is small. If it is negative, the spring force will be lower when the distance from the center position is high. So if we equate spring force with frequency, frequency is going to change as our mass moves up and down based on the strength of this nonlinear response. What will that actually sound like? I'm using X to define my frequency, as we did before, and let me bring up this nonlinear control now. You can start hearing that frequency shifting. We'll bring it all the way up. As the mass moves up and down, you can hear frequency changes. If we move in the opposite direction, we'll shift in the opposite way. All positive, all negative. So this adds dynamic frequency adjustment to your sound. It almost has a spring-like sound to it. Now, one of the nice things that Christophe pointed out is if you make one of these low and the other one high, If we max one of these out in one direction and make the other one kind of high, you can accentuate this. We can hear, since we have the non-linearity set high in viscosity, the effect of this is emphasized in the low register. Well, this has gone on far too long, but maybe we'll end with a more practical programming example. We've kind of been using this kinetic model with this fixed pulse trigger, almost like an oscillator. We haven't really done very much with it. Let's see if we can program some of the kinetic model parameters into the model itself. Remember, I can define up to 4 of my parameters which can be programmed in the matrix. Let's start out with viscosity. What we'll do is we'll program this so that y affects viscosity. Remember, if you program on one of these parameters, it will add whatever you're doing to the base value that's set in the kinetic modeler. So we'll define a little formula. Let's start with a pretty low viscosity. We have our spring constant non-linearity set. We'll keep that. What we'll do is create a formula on y. We'll make this linear. That will go from 0 to maybe 0.64, and we'll apply that formula to our viscosity line. So we'll add up to 0.64 to a value that starts at 0.06. So I'll get up to 0.7 as my max as I go from bottom of y to top of y. And what this will do is, as I increase y, I will increase viscosity. I'll increase that damping. There's bottom of y, which is even longer if I go lower. So let's do that. And let me go up y now. I can hear as I go up y, I damp. Let's program one more. What might I also do? Maybe we'll make mass be dependent on z. So we'll do another formula where I'll increase z, and I can increase that with one of my shapes, either exponential or linear. Let's make it exponential. And what I'll do there is set that to a max value of 0.4. Now I'll define mass, and I'll put my formula on that. So as I press harder now, mass should increase. And as mass increases, we know the frequency should get lower. There, I'm pressing harder, and I can hear I'm getting lower. I'm pressing lighter, and I can damp that as I go up y. I think you get the idea. It's a very powerful model. We've only scratched the surface, applying a very limited selection of functions. In the next video, we'll dive deeper and go into some of the parameters we haven't talked about and how they interrelate with all the other parameters.